Okay. Okay.
Did,
Roman, should I start?
Yeah, so let me say a few words. Today we are pleased to have Aleksy Tralle. He is our distinguished speaker, and he will give a talk on orbifold constructions of Sasakian structures on Smale-Barden manifolds. Thanks a lot for coming, and the floor is yours.
Okay, thank you very much. So I hope now I can I hope everything. Yes, I'm trying to, but well, there's oh yes, it's just it.
It's fine, Alex. Don't worry. So it's fine. Yeah.
Okay, so this is the title of my talk. Well, I of course I stress this orbifold structures, and maybe the title that Roman said was better, but for some mysterious reason I've written this way. But it's the same talk. So about Sasakian structures, and so what I want to begin with is just make some plan. So my plan here is to present some reasonably general theory of Kähler or symplectic orbifolds and Seifert bundles, and then describe some existence problems in Sasakian geometry and present some application of 1 to 2. Yes, so using this theory of Kähler and symplectic orbifolds to get some answers to problems about the existence of some particular Sasakian structures. So well, there are several results obtained by the same or similar methods. So I give some sample of results, and then I try to make a very rough description of methods of proofs. The point is that, of course, this is a joint work with Vicente Munoz and Matthias Schitt, which they are more algebraic geometers. So some of these results will be slightly a bit like black box because there are some methods which are purely algebraic geometric, but nevertheless I will try to do my best. So so maybe, of course, everything is well known, but nevertheless I would like to fix some notation. So I consider contact forms, so a contact odd dimensional manifold of dimension 2n+1 with eta one form satisfying the usual condition, which yields a contact form everywhere on M. And then everybody knows, in fact, that then, of course, you can write this equation, eta of xi equals 1, and the interior product of xi with the differential of eta equals 0. So this vector field exists, and it is called the Rep vector field. And so because it's a vector field, so it determines a one-dimensional foliation, which is called characteristic foliation. And then, of course, the decomposition of the tangent bundle into the kernel and the one-dimensional bundle tangent to xi. So this is notation fixed, and then maybe still it is nice to start in a elementary fashion. So examples which can be easily presented is, for example, the just Euclidean space of dimension 2n+1. And then if you take these coordinates and write down eta in this way, this is a global form, and you just using anti-commutative relation, you can easily see that eta wedge product with d eta to the nth power is not 0 anywhere, everywhere. And so the second example is a sphere, which is odd dimensional, and then you take the form eta of this expressed by this equation, and then you restrict this. So these are coordinates in R2n+2, but you restrict this form to the sphere. And then one can easily, again, calculate this first in Euclidean space. But then if you take the form beta and multiply it with theta times wedge d theta to the nth power, you can see that then you get these coordinates xi square plus yi square, and then it means that it's 0, so on the sphere. So you see that then, of course, the form cannot be 0. So this way you get two obvious examples of contact forms. And then finally, I will define Sasakian manifolds. Although, in fact, I won't be working with tensors anywhere. I will easily go to some another representation of Sasakian manifolds, but nevertheless, the definition which somehow is a definition which makes all these structures on a odd-dimensional manifold compatible. So it's 5-tuple M, G, Xi, eta, J, where we know that G is a Riemannian metric, Xi is a Reeb vector field, eta is a contact form, and J is an endomorphism which satisfies the properties that J to J square equals this right expression minus identity plus the one tensor psi tensor eta. Then you have the form d eta, which is invariant with respect to J. And then also this inequality d eta of Jxx is greater than 0, where for any x which is in the kernel of the form eta. So the next condition is that Xi is killing. With respect to the Riemannian metric, you can see that this G defined as the right-hand side is a Riemannian metric. And then you take a contact cone of this type and define a true almost complex structure just by these formulas, where I of x is J equals J of x on the kernel, and then you need to define I on vector field Xi and on the vector field on R plus, it's T d over dt, and so you see these formulas. Here's how to get it: I square equals minus identity. And so then the Sasakian means that this almost complex structure is in fact integrable. So Sasakian manifold is defined in this way via contact cone. So it's a condition on a contact cone. And though, of course, the definition is quite long, but it is this is a odd-dimensional analog of Kähler manifolds. Yes, so these conditions of compatibility with Riemannian metric are very essential. And so how will we think about Sasakian manifolds? I would like to look on Sasakian manifolds from a different angle. So consider something which is called Booth-Bewang bundle. So you begin with a symplectic manifold, but we want that our symplectic form is integral. So the cohomology class is integral. And then because we have this omega, which is integral, we can assign to this pair, we can assign a principal circle bundle determined by omega. So omega becomes a first Chern or Euler class of this principal circle bundle. And so the theorem, which I will formulate, is as follows, and I will make a hint how to get it. The Booth-Bewang circle bundle admits a K contact structure, and if X omega is scalar, then M is Sasakian. Oh, okay. I think it will be in order to make some remark which I forgot. So if you remove the last condition, the integrability of I, then you get a K contact structure. So it's somehow is closer to symplectic geometry than to Kähler geometry. if you do not demand that I is integrable. If it is almost complex structure only, then you have a K contact. You have a K contact structure. Okay, so as I said, if you take a would-be-one circle bundle, then it admits a K contact structure, and if X omega is scalar, then M is Sasakian. So this is a kind of thinking about some examples of K contact or Sasakian manifolds. Take a would-be-one circle bundle. Well, an easy example is, of course, the Hopf bundle. That if you take S2n+1, a sphere which is considered in Cn+1 as all vectors with norm 1, then you can define the circle action on this sphere by multiplication, by complex multiplication, and then the orbit space is just a projective space, and you can see that this is a free action, so you get a Hopf bundle. And then, according to our theorem, this is an example of a would-be-one bundle, and you have a Sasakian structure on S2n+1 from different point of view. And now, how to explain? It's a kind of explanation, which I omit the details, which are quite long. But there is some theorem proved by Kobayashi that if you have a circle bundle, then you have a connection form such that the pullback of this scalar or symplectic form is d eta. And then you can see that eta must be a contact form, since d eta it's non-degenerate on the horizontal distribution because of the previous equality. So it's non-degenerate. And then taking this horizontal distribution, one can define a Riemannian metric on M in a way to get a Riemannian submersion with totally geodesic fibers. And this means that the Xi is a killing vector. So the Lie derivative of G along Xi is equal to 0. And then the integrability is quite not easy task. Well, it's some kind of non-trivial calculation which I omit here. Then you just calculate the Neuenhuis tensor, and then you get this, that it is if J is integrable, then I is integrable. And then so here is a kind of say not very precise explanation why would-be-one vibration give us K contact structures, and if you take X as a Kähler manifold, then you get a Sasakian. So for us, the first basic example for us is a would-be-one vibration. Okay, so this is just a reference. It's a very old paper, which is in a sense not so easy to read, because it's quite now this language is it's quite archaic, I would say. But nevertheless, you can trace all this in this paper. And so now let us think about these Sasakian manifolds in the context which I have explained. So in the context of would-be-one vibration, there is a Rucambira's theorem that if a manifold admits a Sasakian structure, it also admits a quasi-regular Sasakian structure. And I won't formally introduce quasi-regular Sasakian structures, because I will say something like that. The quasi-regular is the same as being Seifert bundle of a Kähler orbifold determined by its orbifold Kähler class. So instead of not very informative definition of quasi-regularity, I will explain what does mean Seifert bundle, what does mean Kähler orbifold in this context, and then and what is a orbifold Kähler class. And then for us, we will understand Sasakian manifolds exactly in this way. as Seifert bundles over Kähler orbifolds. Why it is important for us? Because the problems which we are considering these are problems about the existence. So in fact, we can, in our context, we can always assume that we have a quasi-regular Sasakian structures. And so we somehow forget, at least now, we forget about the formal definitions. Instead, we are just looking for Seifert bundles over Kähler orbifolds, and these are our understanding of Sasakian manifolds. And so, what is our aim? Maybe I will repeat it again. We want first to create a reasonably general theory of Seifert bundles over Kähler orbifolds and use it to solve some existence problems in Sasakian geometry. And so my small advertising, maybe it's not clever to advertise it in this audience, but nevertheless. So I like this Sasakian geometry because there are some reasons which I have chosen at random. Well, the structure is a tool to construct eta-Einstein metrics. Quasi-regular Sasakian structures is a tool to construct Einstein metrics or Sasaki-Einstein metrics. And there are some other, say, derivatives of this result. For example, every simply connected Sasakian-Stein manifold admits a killing spinor. This is a Friedrich-Katt theorem. So all these results have applications in mathematical physics, especially in general relativity, supergravity theory, supersymmetry, etc. On the other hand, there are abstractions. This is what I would say that for me is very important. On the other hand, there are obstructions to the existence of Sasakian structures. For example, there are quite subtle polar abstractions in dimension 5. We will come across this. So the conclusion is the existence problems for Sasakian structures yield interesting mathematics, just because there are abstractions. So not any manifold, even dimensional, admits Sasakian structure. And so maybe it is reasonable to look at something. And so I will begin again with some definition of orbifold, which is maybe also known, but I would like to write some things explicitly. So formal definition is well known. So X is a Hausdorff paracompact space with some atlas, and atlas is understood as follows: that UI tilde are open in Rn, so or Cn is a misprint, Rn or Cn, and these are finite subgroup gamma I in GL and R, such that UI, these are orbit spaces of UI tilde, and the projection phi is a projection from UI tilde to UI. It is equivalent with respect to the action of gamma I. Gamma I, these are groups acting properly on UI tilde. And so then X is covered by the images, that is by UI. And we have, of course, relatively understandable compatibility conditions. So we have this analog of a manifold. Yes. So what we have on the intersections of our charts. So there should be some UK, and you have this transition maps lambda I k from UK tilde to UI, which must commute with the actions of gamma k and gamma I. So this is a formal definition. So our atlas is considered as an open subset in Rn or Cn, but then there are finite groups gamma I acting on UI tilde, and then the compatibility conditions should be introduced in this way. So it is almost the same as for manifold, but we need to we need to make it compatible with the actions of proper actions of groups gamma I, which we assume to be finite. And then we will consider in this work, we will consider only cyclic 4 orbifolds. So for us, a cyclic 4 orbifold will be a topological Hausdorff space with atlas determined just by C2, and these all gamma I are cyclic groups of order M, and then of the same order M, and this action on Z1, Z2 on C2, yes, this action is given by the explicit formula. So psi to the J1 power Z1, psi to the J2 power Z2, and the greatest common denominator of G1, G2, and M equals 1. So they are mutually prime. So let us see. So this is our basic object. The basic object which we want to consider is cyclic orbifold. So any space with such atlas. This is what we want. This cyclic orbifolds will be considered. So maybe examples of orbifolds. Just
sorry, may I ask you, the J1,
yes?
J2 were fixed, or I didn't understand it properly?
Wait,
J1,
one more.
The J1, J2 are fixed for each psi, or I have a psi as a generator in C.
Wait. Let me
I
think. Yeah,
sorry,
yeah, they are fixed.
Mm-hmm.
So let us think about some examples. So the simplest example, of course, if M is a manifold, a gamma X on M properly discontinuously, but not freely, then P has finite isotropy, and because this is a proper action, then by taking smaller neighborhoods, we can assume that this is that gamma UP tilde intersection with UP is empty, and so then you get that if gamma is not in isotropy, and then if gamma is an isotropy group, then just it preserves the whole, and so finally UP is this orbit space for gamma P. And then this UP yield an orbifold atlas on X. So it's one of the basic examples of orbifolds. And here's another example. C2 is a Riemannian sphere. So we have this atlas phi 0, phi infinity. And if we define this way, phi 0 of Z is Z to the M power, phi infinity of W equals W minus N, and lambda is in this way. And then you can take the cyclic group, say, of roots of unity, and then you will get gamma. Yes, in this way. So we can construct an atlas. And by the way, in some cases we will use this type of understanding. So constructing atlas from an atlas on a manifold. So then because we have an atlas, we have the geometric structures on orbifolds. And so if you have our orbifold atlas, orbit tensor is a collection of tensors on each U alpha, which is the only difference with manifolds is that now we want these tensors to be gamma alpha invariant and agree on intersections. And in this way, we get the definitions of orbit differential forms, orbit Riemannian metrics, orbit almost complex structures, orbit Kähler metrics. And so, well, it maybe it needs some more explanations, but nevertheless, it can be done this way. And then what for us is important is a kind of description of regular and singular points of an orbifold. So if we take our any point x and the chart around x, then we have the order of the isotropy subgroup, and so it is called the order of the isotropy. We consider 4 orbifolds whose points are divided into regular, that means the orbit, the isotropy is trivial. So the order is 1, isolated singular isotropy points, and singular isotropy curves with multiplicities mi, that is, there are di with all x in this curve, or say, if we are in a real world, then we should say surfaces, yes? So maybe we can we can have singular or regular, but singular may be either isolated, or we consider cases when these are singular curves. So all points of these, say, surfaces or curves are have non-trivial isotropy, and this the order of this isotropy is the same mi for all points in di. So these are our, say, singularities. So the singularities are of these 3 types. So 2 types, because regular, it means that fm of x equals 1. So we divide these points this way, and so then we can kind of local models of our 4 orbifolds. So remember that we have these charts, and so the models are as follows. We can consider this the action of our psi on z1, z2 in this way as usual, and then we want that m1 is the greatest common denominator of j1 and m2 is the greatest common denominator of j2m, and so also the greater this m1 and m2 must be so the orders of these points must be mutually prime, and then because of that we have these identities m1 m2 d equals m1, j1 equals m1 e1, j2 equals m1 e1, m equals m1 c1 equals m2 c2. It's just our assumptions, but then according to what relations we have, we make some different models. So for example, if the greatest common denominator of G1 m equals 1 and also GCD of G2 m equals 1, then we get that psi to the power G1 Z1, psi to the G2 Z2 is a misprint, G2 Z2 never equals to Z1 Z2 except the point 0 0. So the quotient is singular, yes, so you must divide C2 by Zm, and then m1 equals 1, m2 equals 1, and it means that x is an isolated singular point. So if we look at the local model of an isolated singular point, then we have C2 divided by Zm, yes, and so it's not C2, yes, it's isolated singular point. But if we take m1, m2 greater than 1 and d equals 1, then m must be m1 times m2, and the Zm action on C2 is equivalent to the product action, Zm1 times Zm2 on C times C. So it's just homomorphic to C times C. And so the third type is assume that fixed points are not isolated. And so then we somehow distinguish the following type. they form transversal surfaces. D1 is Z1 0 and D2 0 Z2 because these are surfaces locally, of course. Then we see that they are transversal and these are non-isolated. And so according to these local descriptions, then type 1 is non-smooth. Yes, we call it non-smooth because you see C2 divided by ZM. But type 2, we call this smooth points. There are more possibilities, but they fall into smooth and non-smooth cases. I just mentioned some, but it is just a local model with respect to the action, with a cyclic group action on Z1 times Z2. So if we take this kind of integers, you will get this type of local models. And so let us first consider the simpler case, smooth for orbifold. So the definition is, we say that a singular point X is smooth if U is homomorphic to a ball in R4. And so we somehow make some description by the following proposition. Let X be a smooth-oriented four manifold with embedded surfaces di intersecting transversely and coefficients mi greater than 1, such that they are mutually prime if they intersect. Then there exists a smooth orbifold structure on X with isotropy surfaces di of multiplicities mi. It took me a long time to understand that how to construct smooth orbifold. So we just take a manifold, but declare some embedded surfaces intersecting transversely, choose coefficients me, and construct just taking the atlas of a smooth manifold, but then introducing the action of a cyclic group, just as as was described before, and you get on the same manifold, you get another structure, which is a smooth orbifold structure, and with isotropy surfaces di of multiplicities mi. So this group acts in a way that di are isotropy surfaces. But, this is a proof, of course, which I wouldn't say that it's a proof, it's just a kind of explanation that use the manifold atlas for all points not in D. And then use the Riemannian metric on a manifold, normal bundle for open V, and trivialize and define the M action on U. It's more or less saying how to construct the atlas. And then this can be done. So if a symplectic this is a version. If we want to have a symplectic orbifold, then take basically the same. Let M omega be a symplectic four manifold with symplectic surfaces intersecting transversely and positively, and then there is a smooth symplectic orbifold structure on X. So what I say is the same proof as before, but you first take a manifold symplectic form and compatible Darboux charts, and then check that the action which I described before makes also gives us an orbifold atlas. And then let us think how to construct a non-smooth Keller orbifold. So remember that we can easily construct smooth Keller, or easily, maybe not easily, but we can construct smooth orbifolds just by choosing di, mi, and an action of a cyclic group, and we get a smooth symplectic orbifold. But if we want to have a non-smooth, which also has isolated singular points, this is a bit more difficult construction, but nevertheless, what we want, a cyclic singular symplectic orbifold. So singular points are isolated, and then they are non-smooth. And we want also to have embedded symplectic surfaces which intersect nicely. it means that locally di is z1, 0, and dj is 0, z2 in the Darboux chart. And then theorem, which was proved by Munoz. Let X be a cyclic scalar for orbifold with a set of singular isolated points. Let di be embedded curves intersecting nicely. Take coefficients mi, the same as before, and then there exists a scalar orbifold structure X with isotropy surfaces di of multiplicities mi and singular points. So what is new is the adding singular points with this multiplicity. This is a technically more difficult theorem, but in the same fashion. Just to describe the atlas. And then finally, I might be running of time, but anyway, now we are coming to Seifert bundles. Again, this is a definition which somehow is quite close to circle bundles, but nevertheless, we use this orbifold atlas. So let X be cyclic oriented for orbifold. A Seifert bundle over X is an oriented 5 manifold, but pay attention that it might be a manifold, oriented 5 manifold, endowed with a smooth S1 action and a continuous map such that for an orbifold chart, there is a commutative diagram. So it must be a manifold, but also must be an orbifold chart. And then this commutative diagram means that the M action on S1 by multiplication, everything is commutative. This is a formal definition of a Seifert. And again, we would like now to have some invariants of Seifert bundles. And these invariants are, so we have our orbifold X, we have P, it's a set of isolated singular points, and we have something which is called a branch divisor. Branch divisor, I would say I don't want to interpret it in other way than just saying that it's this formal expression. This is a formal expression of the right-hand side. So 1 minus 1 over mi, where mi, these are multiplicities, yes, and di our surfaces. So it's a divisor. It's in the usual way of understanding this in algebraic geometry. This is a divisor. And so these are our formal data. X, an orbifold, surfaces di, and the set of isolated singular points, and the branch divisor. Delta is called the branch divisor. And so for each point X with multiplicity M, we have an adaptive chart with the following action. And we call Jx this triple of numbers, of integers. M, J1, J2, we call the local invariants of X. And now if we take our isotropy surfaces with multiplicities M1, D1 with M1, then we assume that each singular point lies either does not belong to any single isotropy, to any isotropy surface, or lies in a single isotropy surface, if any. So the local invariant of D1 is by definition this pair of integers, M1 and J2, where J2 is considered always modular M1. And this is a so-called compatibility condition. So this is a condition which somehow relates the local invariance of isolated singular points with surfaces which consists of also of singular points. And the final, these are these numbers, M, J1, J2, and M1, J2 are invariants of Seifert sorry. Sorry. Of our Orbifold, and now if we want to have some invariant for Seifert bundle, this is an analog of the first Chern class. So for circle bundle, we always can consider, have in mind a bit easier case of circle bundles, and circle bundles are fully described by the Chern class. So we want the same for orbifolds, but for Seifert bundles. But then we have no integral Chern class anymore, but we have a rational Chern class, and it is defined as follows: given a Seifert bundle, we consider the order of stabilizer in S1 and 1 of any point in the fiber over X, we denote it by M of X. And for a Seifert bundle, we define the first Chern class as follows: it's just the least common multiply of all mx, of all orders of all points of x. And then denote by m divided by L, the quotient of m by this ZL, where L is this least common multiply. And then if we divide m by ZL, we get a true fiber bundle, and then we will get the first Chern class of this circle bundle, C1 of m divided by L. This is, of course, the usual integral Chern class, and then we define this C1 of m just as 1 divided by L of C1 of m divided by E, and so it is a cohomology class in the second cohomology group over the rationals. And then this is our invariant. So it's an analog of a first Chern class for true fiber or circle bundles. And finally, this is a theorem which we proved with Vicente Munoz. So what is the construction for Seifert bundles? For Seifert bundles, we have the following: let X be a cyclic for orbifold with a complex structure, and di complex curves of X which intersect transversely. Choose this mi as before, and suppose that there are given local invariants for each di and a local invariant jp for every singular point. And the compatibility condition is also satisfied. Choose any integers bi between 0 and mi such that this gi times bi is congruent to 1 modulo mi. And let B be a complex line bundle over X. Then there exists a Seifert bundle M with a given local invariance and the first orbifold Chern class C1 of M expressed by this formula. Here, of course, you should understand this, that di in fact are dual cohomology classes, but we don't care because it's the usual algebraic geometry somehow tradition. We just don't write this, but of course, because these are cohomology classes, then we take the duals. Moreover, if X is a Kähler cyclic orbifold and C1 of M, C1 of X, sorry, it's a misprint. C1 of X equals let me think. Yes, C1 of X for the orbifold Kähler form, then M is Sasakian. Then M is Sasakian. This C1 of X is Sasakian. It's a misprint. Finally, what does it mean? It means that if you take a complex line bundle over X with C1 of B and write down this C1 by this formula, then you get always a Seifert bundle with this orbifold Chern class. So what is somehow our data? Bi, Mi, Di, and then you can construct it. So if you choose any of these numbers and homology classes which are compatible in the sense below, you can always have a Seifert bundle. So this is most important technical thing, that you can always do it that way, and you have some kind of flexibility for Bi, Mi, and we play with this all the time. This theorem is the basic theorem. We play the whole game just using this formula. And so maybe a small comparison will be in order. So would be one vibration. Yes, this is just take a homology class. If we want to do the same for orbifolds and Seifert bundle, we need more. We need X, P, branch divisor, data M, G1, G2, and take this C1 M, but then you get the same. Then you get the same. You have the orbifold, say, would be one vibration, I would say, yes. But the formulas are much more complicated. But what is the gain? The gain means more flexibility. One wants to choose local invariants Mi, Ji, Bi, P, delta in an arbitrary way, ensuring, however, to be represented C1 of X again should be represented by some Taylor form, and that's our basic tool. And finally, Smale-Barden manifolds. This is the first interesting dimension for our approach. The 5-dimensional simply connected manifold M is called the Smale-Barden manifold. These manifolds are classified by the second homology group Z and the Barden invariants. So how to classify them? Write the second homology group as a direct sum of cyclic groups of prime power order. That way, K is the second Betti number of M. I of M is the smallest integer J, such that there is alpha in the second homology group with the value of the second Stiffer-Whitney class over alpha not 0. And alpha has order 2 to the J. I of M is called the Barden invariant. So finally, this is somehow very unusual, yes, because in general, cohomological invariants do not determine manifolds up to diffeomorphism. But this is the case for 5-dimensional simply connected manifold. This data, so the second homology group and I of M, completely determine a manifold up to diffeomorphism. And this is so interesting in this situation, because on one hand, we can understand M completely if we know this data. But then very natural question is, if I look at this data, can I say when this data determine the existence of Sasakian structure or not? So any Smale-Barden manifold is uniquely determined up to diffeomorphism by this data. So Smale-Barden manifolds are classified by the second homology group, torsion groups, and I of M. And so then maybe I will skip this because I think everybody knows what is basic cohomology, yes, for foliated manifolds. So I will skip this, but then one definition which I would like to, because in a moment I will formulate the question. So this is a notion of definite Sasakian structures. So let Fxi be the characteristic foliation of the Reeb vector field, and then take our decomposition of the tangent bundle. But since D is a complex vector bundle, so there are basic Chern classes. And the definition is a Sasakian structure is called negative if this basic first term class can be represented by a negative definite 1-1 form, and it is called positive if it can be represented by a positive definite. It is null if C1 of f psi equals 0. And then finally, I will formulate some questions. These are open problems, which some of them were solved by our methods. So it's a very seminal book by Borer and Galitsky on Sasakian geometry. There is, of course, some fundamental question: which Smale-Barden manifolds admit Sasakian structures? Because this is the most interesting question. You can have the whole data. These are just homology and torsion in homology groups and the Barden invariant, and then is this manifold Sasakian or not? The second question: are there Smale-Barden manifolds which admit K-contact but do not admit Sasakian structures? This is my favorite question. It is a Sasakian analog of the question in symplectic topology. Are there symplectic manifolds with no Kähler structure? So the same question is for Sasakian manifolds. This also interesting question in the same context: which simply connected rational homology spheres admit Sasakian structure? And a weaker: which simply connected rational homology spheres admit both positive and negative Sasakian structures? And why this question is because basically, if you look at the classification of Smale-Barden manifolds, then this is one of the basic types which appears. These are just connected sums of S2 times S3. So determine when this manifold admits a negative Sasakian structure, and determine when this manifold admits a null Sasakian. So all these questions were posed in the paper, in the book by Boyer and Galitsky, and they were open until we somehow found some approach to these problems. So I will now give a sample of results. So this is a paper of myself, Vicente, and Matthias, a negative Sasakian structures on simply connected 5 manifolds, and where we give complete answers to questions 4 and 5. In greater detail, I will just only recall this 4 and 5, which simply connected rational homology spheres admit both positive and negative Sasakian structures, and determine when this connected sum admits a negative Sasakian structure. So in greater detail, we give the complete answers to questions 4 and 5. It's just a sample. We have more results, but this is a sample. Theorem 1. Any simply connected rational homology sphere admitting positive Sasakian structure admits also a negative Sasakian structure. And theorem 2. Any connected sum of this admits negative Sasakian structure. And so now maybe I have still 6 minutes. Maybe I will very, very briefly explain what we well, maybe I will skip some context why this question is so important. This come from some Kohler results, but maybe on a Sasaki-Einstein manifold. But nevertheless, I just skip the context, and so how we want to prove our theorem. So to answer to question 4 on this negative and positive Sasakian structure, one need to construct a manifold with B2 of M equals 0 because it's a homology sphere. Yes, because it's homology sphere. So the second Betti number of M should be 0. And because of Kohler's theorem, we know that there are restrictions on torsion groups in the second homology. But now we want to take such manifold with B2M equals 0 with this prescribed by Kohler's torsion groups in the homology, and then somehow construct negative Sasakian structure. How we can do this? So this is a general scheme of proof. We know that we can restrict ourselves to Seifert bundles. over Kähler orbifolds by Rukimbier. Then there is a method, I didn't explain it yet. There is a method, say, of Kähler's type, because we, in a sense, we just extend Kähler results to non-smooth orbifolds. There is a method of Kähler's type of calculating the homology of M from homology of X, and in particular, we can calculate the second homology of M. And then we construct a Kähler orbifold and Seifert bundle such that H of X and H of M has prescribed B2 and the torsion groups. And the rather difficult part of proof is to prove that it is Smale-Barden, so that the fundamental group of M equals 1. If such X is constructed, then we, for free, we get M as a rational homology sphere or this connected sum. And so, but now we somehow need to express in these terms the negativity condition and check that it is compatible with the other data. So we just, well, it's a quite tedious work of making all this compatible. So by my theorem with Vicente, we know that we can construct Kähler orbifolds, but then we need patiently do all these calculations to somehow make sure that all these conditions are compatible with our data. And so a method of constructing such orbifolds is taken from algebraic geometry. We have, I will skip all this. We just take a smooth complex surface with some configuration of curves, with some self-intersections. And then we know from some other work of algebraic geometers that in this way, if we take our rational curves and blow down them, we'll get an orbifold. And all these constructions come from algebraic geometry. And then we somehow prove all this and use Kähler's, first we prove some analogous of Kähler type results on homology and calculate homology using these theorems. And finally, we use some algebraic geometry stuff in the version for orbifolds and use the following result of Boyer and Galitsky. A manifold admits a quasi-regular negative Sasakian structure if and only if the base X of the Seifert bundle has the property that the canonical class, so this is orbifold canonical class, is ample. And then we use the Nakai-Moishazon criterion and just check this condition that this orbifold canonical class is ample. And I will skip all this, but the key points are to guess what smooth algebraic surface to take, and using this algebraic surface, choose a chain of curves in a way to get an orbifold by all these constructions which I explained, and the flexibility is ensured by the choice of local invariance, because remember that we can choose our local invariance. This was the main contribution, in fact, that we could manipulate with our local invariance, just integers, in a way to get the branch divisor, which yields us the ampleness condition, and that's all. So this is what we did. So it's an example of the choice of this branch divisor. You just have a look at this. We just manipulate with integers. This somehow exciting. This my collaboration with algebraic geometers is exciting because you just manipulate by integers and you get the result. So this is what we get. So this is the ampleness condition. The ampleness condition just means that all these coefficients must be positive, and you ensure positivity just by taking the appropriate m, n, and mi. So it's very funny. So I will skip all this. This is some references. So all these papers, all these results are published. So maybe you can, if you are interested, you can look at this. And recently, I was asked to write a survey on this topic. So there is a survey of what I was talking today. Some topics in Sasakian geometry. So maybe it's just if somebody is interested. Maybe my talk was a bit chaotic because there is a lot of technicalities, but maybe I can refer to this survey as well. So sorry for maybe some chaotic explanations. Too many technicalities. Thank you very much for your attention.
Thank you very much, Alex, for the great talk. Are there any questions, comments, remarks?
Well, I think it's quite technical, yes. But
I ask you
yes.
that you say that from symplectic manifold it's how to say integral or rational.
Yes.
You can construct how to say Both-Banden with a K contact structure, right?
So sorry, once more, please. What
associate with a manifold with the integral structure?
Yes.
Both one fiber bundle, and you say that this fiber bundle admits K contact structure.
Maybe let's see.
K contact structure on the
complex structure on what?
On the Both-Banden vibration, very beginning.
Yes. Both-Banden vibration, yes.
Yes, but then you speak only about Sasakian structure, right? So
let's maybe go back in a moment. So if we have this Both-Banden vibration, yes.
Yeah.
So this is yes. If this omega is integral, then you have just a principal bundle with this Chern class.
Yeah.
Yes. And now, if we want to have a so I understand your question that you mean what is going on with the Seifert bundles, yes?
Yeah, so that means that you can use this a thing to study symplectic underlying manifold or not. Of course, because you say that
if you take symplectic, yes, you will get K contact. It's also known. I mean that if you take this, do the same, but you don't require that X is complex and just say that X is symplectic. You can do all this, but then you will get only K contact.
But then can you get some of course not so strong reason, but some non-trivial reason. That means that then you got some new reason for symplectic.
Well, in a sense, yes, because in the context of K contact structure, we also have results on this problem of Boyer and Galitsky. Are there K contact manifolds with no Sasakian structures? So maybe I will point out the following result of Mayen and Vicente, and later result of Vicente himself without my participation. Let me show you this reference. Oh, here it is. You can look at the paper Homology Smale-Barden manifolds with K contact, but not Sasakian structures in International Mathematical Research Notices, where we exactly do this. We use these constructions to get such manifold, but we cannot. In this paper, we could not be. We were not able to prove that the manifold we get is simply connected. it has the same homology as simply connected manifold, but this is a weaker result. But later, Vicente published a paper with full proof with the same, say, ideology, with the same idea, but he managed to complete the case. So there is a result of Muniz. I think it may be already published, but I'm not sure. It was accepted in the Journal of European Mathematical Society, but I'm not sure. But certainly there is it's in archive. You can look at the full proof, but this proof in this paper it's a bit easier to read because we work only with smooth orbifolds. But anyway, you can consider K contact versus scalar. Yes, this is what can be done.
Alex, could you please explain once again where do you use ampleness? And can it be, for example, substituted
yes,
with a semi-ampleness or something like that?
Yes. I will again. I will go back to you see that here is the theorem of Boyron-Galitsky. Manifold M admits a quasi-regular negative Sasakian structure if and only if the base of the Seifert bundle has the property the canonical class is ample. And so this was, in fact, we used this theorem a bit like a black box. We just say, okay, if it is this way, then we just need to construct something which we know that the orbifold canonical class is ample. And then so in a sense, this result which we obtained was obtained by, in fact, algebraic geometry methods and not by differential geometry methods. We just put it for granted, took it for granted that well, if it is the same, then okay, then we can check it.
Because ampleness could be difficult to check.
Yeah, basically it's difficult. Yeah, but what is a simplifying way is because it's orbifold, and you see this extra term. It's delta. It's branch divisor, and you have a big possibility to change this mi and m. That was the play.
I see. Thank you.
Can you give reference to the Boyer-Galitsky theorem?
Yes, well, it is in the book Boyron-Galitsky Sasakian geometry. Well, I don't remember the page. If you
no, it's okay.
I have the book on my desk, so I can tell you. But it's in the book.
I will borrow it. Thank you.
So,
okay.
If there are no other questions, let's thank the speaker again.
Oh, thank you all. It was great to hear all of you again. So I hope we'll meet maybe in Cerny or somewhere else. So thank you very much for your invitation.